Okay, in the last page, we just talked about even if their starting positions are different, you could have two vectors, two position vectors actually be the same in value if their x and y components are the same. So in this case, if equality of vector theorem, two vectors v and w are equal if and only if their corresponding components are equal, meaning the x component and your y component. So v is made up of a1 and b1. Those are our two values that we're doing. And w is made up of a2 and b2 because it starts somewhere else. Then v is equal to w if and only if your a1 component, meaning how long it is equal to how long your other one is. And how high or low it is the same as the other one's how high or low, right? So if one starts here and goes, and one starts over here and goes, but they both have the same x and y components, then they could be equal. All right. We're going to complicate things just a little bit. Unit vectors. Another algebraic way of representing vectors is by using unit vectors, where I, our unit vector for x, is going to be 1, 0. And quite often we'll see I hat, not just I, because the I hat represents a unit vector. And then j, and again, sometimes we'll see the version of j hat. That's how I learned, so we probably will, if I write it that way, that's why. So therefore, if a vector has your x and y components a, b, that a would actually be a times your unit vector and b times its unit vector. So we would call it a I hat and b j hat. Okay, so what this does is it allows us to put it back into that, really it's rectangular format. But then the i's, the j's, and even a k would be next to do the z-axis, would represent what axis we're talking about. Okay, so adding and subtracting vectors algebraically, we've already done it graphically, so you should be good with how we're doing this. So we're going to have v is going to be a1i b1j, and w is going to be a2i b2j. They're two vectors, and alpha is going to be scalar. So alpha is just a number that we're going to complicate things with, right? Okay, so algebraically, and we will do this kind of setup. Like, let's say I have 3 plus 2i, and I'm talking about complex numbers here. And then I have 4 minus 6i. If I want to take those two expressions and add them together, I would end up with negative 4i and 7. 7 minus 4i. We're going to do something similar, but this I hat, j hat, and k hat are going to tell us what axis we're on. Okay, so if I want to add v plus w, I'm going to take my value on the x and add it to the other value on the x. So that would look like this. A1 plus A2, I'm going to add those together, and then that's going to be my I hat. Okay, and then I would add to that my b value, which is my y. So b1 plus b2, okay, b1 plus b2, and then I'm going to throw my j hat on it. So my I hat tells me it's my x value, my j hat tells me it's my y value, okay? And the other way I could write this is I could have the value a1 plus a2, and then b1 plus b2. That's another way that we could write the components. And so now we have v minus w. So just like we added before, we're going to take our a1i and subtract a2i. So a1 minus a2 I hat plus b1 minus b2 j hat. Now, if it had w minus v, then what we would do is put a negative value, on that a1 and then keep the a2 positive. So depending on what it is that you need, okay? So my component notation would be a1 minus a2 and b1 minus b2. Now let's look at multiplying a value, a scalar, that alpha scalar, and coming up with our terms there. So here I would have alpha times v, and that would be I hat, plus alpha times, excuse me, I don't want the v there. I want a1, okay? Alpha times a1, and that's going to be I hat. And then we are going to add to that our y components, and that's going to be alpha b1 j hat. Okay, so what that looks like in notation form would be alpha a1 and alpha b1. And if you multiplied it through w, it would be the same. Okay. Now, our actual value of our vector is going to end up being the square root, right, of our a1 squared plus b1 squared. And if we wanted to find the value of w, that would be equal to the square root of a2 squared plus b2 squared. Okay, so just like how we did of finding our resultant vector or finding the r value, same thing. All right, so the following graphs illustrate these definitions. Okay, so we have a1 and a2. If we add them together, then my x component of this is going to be the same value as them added together. If I take b1 and b2 and I add those together, it's going to be the same as the b value of my resultant vector. Okay. If I do a subtraction, which let's see here, w and v, that's plus. This one is if I multiply, right? So if I have this value of a multiplied by a1, in this case it looks like double, right? I would take however many times we need to draw that vector to satisfy that alpha value. And then this would be just drawing our actual v vector, my point being on the origin, and then a1, b1 showing my components in my x and y direction.